Chapter 1. Pore Pressure and Fracture Gradient. 1.1. Pore Pressure Prognosis. The first step to drill a well is to predict the pore pressure and fracture gradient that the well will encounter. In most cases, the information that is available is very limited, so the main difficulties with oil and gas drilling start right at the beginning. Owing to this fact, some assumptions have to be considered. In new frontier areas, no information is available, only seismic and sometimes in very bad quality. Therefore, only an educated guess is possible in terms of determining the pore pressure of the formations that will be encountered while drilling. In not such frontier areas, some information can be available, like formation tests that provide us with the pressure that was encountered at different depths. The formation tests data can be used to calculate the pore and fracture pressures of the formations above those pressure points, once again assuming certain values. For example, the pressure data can indicate that the gradient from the pressure points to mean sea level is a saltwater gradient of 0.45 psi per foot, which, for example, suggests that no abnormal pressures will be encountered. However, it may have a 1,000 psi increment of pressure below the reservoir top from 5,000 psi at 10,000 feet TVD to 6,000 psi, which could be the known pressure of a reservoir that was already drilled. In this case, we know the pressure of the reservoir, but in some other cases we don't. It is important to be aware of all of these uncertainties when we go to drill for oil and gas. In this case, we would assume the reservoir is overpressured, and this needs to be taken into consideration for the pressure predictions. Consequently, it will affect the whole well design as well as the rig selection. 1.2. Fracture Gradient Prediction. In terms of the fracture gradient prediction, two models are usually considered. One of them is the Ben-Eaton formula, which calculates the fracture pressure from the pore pressure and geostatic pressure, as well as the Poisson ratio. Once again, to obtain a predicted value of the fracturing pressure, the following assumptions have to be incorporated. Poisson ratio equals 0.3. Geostatic pressure needs the following assumptions to be calculated. Formation gradient, 1 psi per foot. Saltwater gradient, 0.45 psi per foot. An alternative, to cross-check your information and make sure you are obtaining sound values, is to obtain local data from wells drilled around the area. Obviously, this data needs to be looked at with a critical eye to ensure it is data from wells that have similar formations, rock, to the ones we will be drilling. In other words, ensure they qualify as proper analog wells. For example, a North Sea typical formation fracture gradient is 0.81 psi per foot, and this could be used as a reference if you were to drill a well in the North Sea. Pressure charts are usually the final outcome of this exercise, with the predictions of the pore pressure, fracture pressure, and overburden pressure gradients that, supposedly, will be encountered at specific depths throughout the drilling of the well. 1.3. Mud Window. The whole purpose of having pore and fracture pressure curves is to have a minimum and a maximum in which we can use a certain density of drilling fluid, also known as mud, to drill the well safely, not exceeding the fracture gradient and not going below the pore pressure. This zone between the upper and lower limits is usually called a mud window. The mud window is given a safety factor to ensure that the limits are not reached while drilling. Usually, the mud window is displayed in a graph with the mud density in the x-axis and the depth of the well in the y-axis, where the pressure and gradient curves are also shown, and the mud window is in between those curves. After obtaining the mud window, we can try to do some standardization of a hypothetical well outline. The following assumptions can be applicable to development wells within a field that already drilled its exploration and appraisal wells, i.e., it is possible to confidently elaborate a well design by applying these assumptions. Note be taken that it is possible to obtain this standardization when an intensive regional geology research is done with good quality data, as well as a significant effort is undertaken to understand local well design architecture. Considering all this, it would be possible to assume tentative casing setting depths, which will later be analyzed and confirmed, or not, in the casing design process. A possible standard configuration for an offshore project with about 300 feet of water depth, nowadays considered a shallow water depth, without any special anomalies in the formations that will be drilled, could have this tentative well configuration. 26-inch phase, 20-inch conductor casing, casing depth 300 feet below WD. 17.5-inch phase, 13 3/8-inch structural or surface casing, casing depth at 2,000 feet, since it was assumed that no drilling hazards were presented in the respective casing setting depth formation. 12 1/4-inch phase, 9 5/8 intermediate casing, casing depth 300 feet before top of reservoir formation. 8.5-inch phase, 7-inch production liner. Liner setting depth should include a 150-foot rat hole after the end of the reservoir to allow wireline logging and possible well testing operations. Note that to drill an oil and gas well, you have to start by drilling with a bigger bit. Then you lower a big casing, and then you go to the next phase, or also known as hole section, and you drill with a smaller bit, and so on, lowering a smaller casing and drilling with an even smaller bit until you reach the reservoir, which is your main objective. The reservoir is the section of your well that has a permeable and porous rock, hopefully with oil or gas, which are both made out of hydrocarbons. If hydrocarbons are encountered, they are lying in the pores of the rock, and the reservoir rock needs to have enough permeability between its pores for the hydrocarbons to flow into the well and to be produced, which is the ultimate objective of oil and gas drilling.